Okay, so let's say you've got your probability distribution function. It tells you the relative probability of some number lying in a particular range. How can you interpret it? What does it mean? Well, there are actually two very different ways of interpreting these things, the Frequentist approach and the Bayesian approach. For much of the last 200 years, the proponents of these two different ways have been insulting each other and fighting, but we now know they're both actually correct methods that are useful in different senses. So let's imagine, we'll look at the Frequentist approach first. Let's imagine we have a probability distribution function that looks something like this. Let's say that you're an engineer and this probability distribution function is telling you the length of car doors that you're manufacturing on your production line. So ideally your production line would make car doors that were all exactly the same length, but that's never going to happen. There are going to be vibrations, changes in temperature, wear and tear on your production equipment and so on, so they're all going to come out a bit different. And this is telling you the odds of it having a different length. So that's the most typical length of the doors, but some of them are quite a bit longer and some are quite a bit smaller down there. Now, one way you can interpret something like this is it'll be the histogram, the distribution of a large number of measurements or a large number of doors made like this. So if you did 10,000 doors coming off your production line, this would be a histogram showing you the relative frequencies of the different sizes. So you can ask, for example, what fraction of doors will be bigger than this? Maybe you don't want them bigger than that because if they're bigger than that they don't fit into the door jamb. And the way you do that is you'd take the line there and measure the area over here. And that area will be the fraction of the doors that do not fit that size. Or it could be that your boss has said, we can only sell doors that were in this range. And in that case, it would be the area in here will be the fraction of doors that pass spec, and all the other area, the other fraction, will have to be thrown away because they don't meet the specifications. Another way to think about it might be, say, a physicist studying gravity waves. So in gravity waves you have an interferometer, so you fire laser beams at two right-angle directions and you bounce them off mirrors back and forth, and when a gravity wave comes through it stretches one of these arms and shrinks the other one. The LIGO detectors have arms 4 kilometers long with lasers bouncing up and down, and a gravity wave when it comes along will slightly change the length of one arm compared to the other as it compresses space-time. So you might get a graph showing the relative length. So this is the relative length. Now let's say there were no gravity waves coming through your detector. You'd expect the relative length always to be 0, but it won't be in practice because there's going to be some form of noise and uncertainty. So in the complete absence of any noise, you're going to get some probability distribution function of lengths. In this case, part of the problem is because of thermal noise, the random vibration of the atoms. Part of it's quantum mechanics, the random arrival of the photons and the lasers, and then there's seismic noise from people walking past, micro-earthquakes, and many other things. So that means even with no gravity waves, you're not always going to get 0. You're sometimes going to get a positive and negative value. Now let's imagine on one particular day a supernova explodes and the astronomers see it. And at exactly the same moment the supernova explodes, you measured a value up here of the relative length. Now does that mean you've picked up a gravity wave or not? Well, what you could ask is, could it just be a fluke? The distribution does not go to 0 out here, so there is some chance that you get a value that high just by chance. In fact, what you do is you add up all the area below the curve above that, and that tells you the odds that you'll get a relative length that big or bigger. And then you've got to ask, how big is that probability? If that probability is quite high, like 10%, then there's like a 10% chance that the the gravity wave you thought you detected was actually just a statistical fluke. But if that probability is really small, like 1 in a million, then you've probably detected a gravity wave. So that's the frequentist approach. The Bayesian approach is a little bit different. It's a way, what it says is that this curve does not represent what happens if you had a million measurements of the gravity wave strain or a million doors coming off the production line. This is more what you use if you've only got one measurement point. And what it's telling you is your knowledge. So the graph doesn't say, if we did this a million times, here's what the distribution would be like. It says, here is what my knowledge about this measurement is going to be. So let me give an example to make it clearer. Let's say you have a ship has gone missing. It set sail from a harbour, sailed out to sea and disappeared. You want to know where to look for the wreckage. So this might be you assume it's going to be on the route it's scheduled to take, and you want to know how far you got to search. Now let's say to begin with all you know is that the ship was last seen at this distance from port, and it failed to make a report at that point. So what that tells you is it sank somewhere between here and here. So to begin with you might guess that the probability looks something like that. It could have sunk anywhere in that range, and you've no idea where in that range it sank. So this graph is telling you something about your knowledge of the ship. It's also telling you that if you had a million ships that all set sail, and all last reported here, and all failed to make a report there, this is a distribution of where they sank. But that's not a very useful thing to think about. But now let's say you get some more information. So for example, about the time when the ship should have been here, let's say a cyclone came through, very bad storm. Now it's quite likely that the ship could have sunk for two reasons. It might have sunk because there was a hijack attempt that went wrong, or the engine failed, something like that. Let's say there was a 10% chance of that, but much more likely is it got sunk by the cyclone. So in this case, we can now update it. We now think that maybe there's a relatively small chance it sank before then, and a rather large chance it sank after then. And now let's say that you've already mapped the sea floor over that region and you haven't seen it. So you now know it's not there. So now your curve might go 0 there, up here, and down like that. And then you might learn that in fact the ship was designed to be cyclone proof, but it had a really dicky engine that was likely to explode. In that case you might bring down the probability of the cyclone destroying it and bring up the probability that it just crashed because of some random error in its engines. And so on. So the Bayesian approach tells you a graph of your knowledge of what something's going to be, and as you get more information in, it will steadily change. Hopefully as more measurements come in, it might get narrower and narrower and narrower. But it doesn't tell you anything about what's actually happening, it's just telling you about your knowledge. Whereas the frequentist approach assumes that you have lots and lots of trials, like lots and lots of measurements or lots and lots of car doors, and it plots a histogram of the two. And they are both useful. If you want to build a lot of things and work out what fraction of them fail to meet specification, or what fraction are too big or too small, then you use the frequentist approach. If you are trying to see whether a particular measurement you've made is a random fluke, or whether it's telling you something interesting, then you use the frequentist approach. If, on the other hand, you're trying to determine something and you make measurement after measurement and you want to see how your knowledge is getting better, you'd use the Bayesian approach, which is used, for example, for things like spam detection and email filters. So it constantly updates the probability that a given email is spam, depending on more and more information as it comes in. Both useful.